Hey Vasan, I have a question about a rack system. Can you help me out? Hey there. Sure. What's on your mind? So, our company's rack system is struggling a bit with a massive corpus causing memory issues and slow retrieval. Any ideas on how to tackle this? Have you heard about the latest feature released from Hugging Face called the embedding quantization? No. What's that about? It's a method to optimize your embeddings for memory and speed efficiency. By quantizing your embeddings, you can retain up to 97% of your original performance while saving up to 32 times on memory and speeding up your retrieval process by a whopping 45 times. Whoa, that sounds fascinating. Can you walk me through to how I can implement it? Absolutely. Let's dive into it. For this, let's start with this blog from the Hugging Face organization themselves by Amir Shakir, Tom Arson, and Sean Lee, where they are introducing the concept of embedding quantization and they are showing the impact on retrieval speed and memory usage. Here are the table contents, and we are not going to see everything. I'm not going to explain the quantization method and all. And if you are interested in that, please let me know in the comment section. I'll try to make a video on how the quantization works. So for this, they are showing two methods. One is binary quantization and another one is int8 quantization. In both ways, they are showing how you can store your embeddings and then how we can use it while retrieval and how much it affects the performance. So those are all shown in the quantization experiments. Okay, so let's start with this, and I hope you all know what is embeddings now. Embeddings are a representation to anything you can see, which is text, image, audios, etc. Embeddings are numerical representation of those. Usually embeddings are stored in float 32 and that always goes into a bottleneck. So for example, here is a very small model known as All Mini LM L6V2, which is taking around $543 for storing 100 million embeddings. So let's say you are storing 100 billion embeddings just with a dimension of 384. It is going to cost you $543 per month, just per month. And if you are going to store 250 million embeddings, then that's all, like, 1400 per month. This is for the basic models. So for example, let's go with a model which is used regularly nowadays in industry and is a very high quality model which we are also using in our channel, which is MXBAI Embed Large V1. For this, if you are going to store 100 million embeddings, it is going to cost you $1,500. And if you are going to make it in Indian rupees, we all know how much it is going to cost you. It's going to be in lakhs. For sure, right? And that is just for 1 month and for 100 million embeddings. So if you are a very big company, like highly scalable, highly scaled product companies, even if you go to 1 billion, right, it is going to cost you $15,000. That is pretty huge cost. Okay, so in this video, I'll show you how you can reduce that and improve your scalability. There was a recent post from OpenAI on Matryoshka. I'm not sure how to pronounce that. Matryoshka representational learning, where they showed how you can use cheaper embeddings and also get almost the same performance. You will retain very good performance, and here they got around 12x compression. Okay, that is the core idea here. And first method which is discussed here is binary quantization. Usually quantization will happen with reducing the precision of weights. And for embeddings, what you will do is you will convert the float 32 values into a 1-bit value, which means every 32 is reduced to 1 bit, and indirectly, even directly as a math, you are getting 32x reduction in your memory storage. Okay, so what they did was just if x is greater than or equal to 0, or sorry, lesser than or equal to 0, it is 0, and if it is greater than 0, it is 1. That's all. Okay. And for retrieval, it is said that you can use Hamming distance for retrieving the embeddings efficiently, and lower the Hamming distance, the closer are the embeddings. Okay, so that is about how you can quantize your model in binary. There are some other things which we won't see. Okay, for code, all you need to do is just add precision equal to binary, and don't worry, I'm going to show you at real time how this works as well. Okay, so let's not go into the codes now. All right, now about the int8 quantization. Before going on to that, we'll also see binary quantization in vector database. See, phase supports, usearch supports, vespi supports, milvis supports, quadrant supports, and VVH supports. So except ChromaDB, I guess all popular vector databases are supporting binary quantization. So now we are thinking, okay, I don't want to use binary, but still I want to reduce. So there is a middle option, which is int8. Okay. So here what happens is, all you need to do is, first it is said that you need to make a calibration set, for which you need to first load a data set, a sample data set, and then encode your questions. Okay, here whatever corpus you have, and then quantize your embeddings of your new model, new data, whatever you have, with the precision of int8, and provide your calibration embeddings as before. Okay, so this could be a source corpus in which your data might fall, and this is your real data set. So that's how you need to quantize. Okay, and here it is said that you can quantize it to int8 or int8 upon your choice again. Okay, usually it is minus 2.0 to plus 5.0, the range, and here it is going to become minus 128 to 127. Okay, so theoretically, what is the performance you are going to achieve is, it should be 4x reduced, because int is in 8 and float is in 32 bits. Okay, so you should at least get 4x memory, but speed, I'm not sure. We'll see about that as well. Okay, here are some experiments which they have performed, it seems. Let's focus on MXBAI. Okay, for MXBAI, if they took 250 million embeddings, which is what they are considering, okay, it is costing around 3,600 per month. Okay, and that is around 55 score. Okay, and the performance now is 100. We should call this as percentile. Okay, now this is first, and we are going to try to match that with the other methods. If you do it in int8, what you're going to get is 230 GB, which is around 905, which is already a pretty good improvement, 4x improvement. 9,900 into 4 is equal to 3,600. So you are reducing the cost by 4 times, and for a compromise of 3% accuracy, which I'll do personally. And then we have the binary embedding, which I'm the most interested in, which is costing just 29 gigs. Yes, 29 gigs, that is around $100. And here it is 3,600, which is around 36 times, give or take. Okay, for a accuracy compromise of 3.5. I'll take it any day, right? See, there are other models also which they have provided, but you can check it out. Okay, the binary rescoring has been said that at least it retains around 93% in MTEB retrieval. Okay, and if you are doing with more samples with retrieval and all, you can at least push it up to 97%. That is what is claimed here. And yeah, I'm also very happy to take 97. Even 95 is something I'll take any day. So same goes for int8 reasoning also. But we talked about 2 points. One is the memory and another one is speed. Now we'll see about the speed. Okay, in float, if you run it right, the minimum speed up you'll get in int8 is around 3x, and the maximum speed up you'll get is around 5x. Okay, let's say you quantize it to int8, you'll get at least 5x speed up. But when you do a quantization in binary, the minimum speed up is itself around 15x, and the max speed up is around 46x. That is pretty amazing. Okay, and here is a very good summarization where in memory you will be saving around 32x in binary, and for retrieval speed up you will get around 45x. So this is an amazing blog. The link is in the description. You can also check it out. Okay, now let's see the code of how you can do this for a RAG application of your own. Let's open a Jupyter notebook. I'll keep it as lightning RAG itself. We'll keep it as lightning RAG. So let's select the kernel. Just markdown validation crew itself is fine. And here we are more focused on the retrieval. Okay, so first we need some imports, and we are going to see those now. Okay, we'll need these imports where to load a text file, you need a text file. For phase, you need a vector store, right? So for that we are using files. We are going to use the LLMs by using chat grok. And for character text splitter, for chunking, we are using recursive character text splitter. And for documents, we are going to use stuffing. We are going to use stuff document chain. For prompts, we are going to use stat prop template, and we are also adding a retrieval chain to answer the question. And finally, Hugging Face embeddings. So here also, instead of this, we shall try PDF. Okay, so I have changed it to PDF so that we can run some PDF here. The first step is we need to make the PDF being loaded. Okay, so for this I'm going to take a research paper, which I'll put it in the GitHub repo as well. So yeah guys, let's start with the code now. And here I have a Jupyter notebook demonstrating the power of quantized embedding based rack system, where we'll see that the time taken will be reduced, but also the storage will be massively reduced, and we are going to see that now. For this, we need the following imports to load the PDF. We are using PyPDF loader, vector store files, grok for loading the LLM, recursive character text splitter for splitting the documents into chunks, and once the relevant documents are retrieved, to combine those together, we need the stuff document string and prompt template to format the input prompt for the model, and retrieval chain to make a QA chain out of the LLMs and retriever, and finally the Hugging Face embeddings class to load a Hugging Face model in order to generate embeddings. Next, to load, we can load the PDF here by using PyPDF loader, and you can see here this is a 17-page PDF, just 17 page. Okay, there is a reason why I'm saying just 17 page. In a 17-page PDF, once we load the PDF, we are chunking it with the help of recursive character text splitter and splitting the documents, which is chunking again. And here you guys need to provide your own grok API key. Make sure that you have provided it there. Then we'll create the embeddings class. Okay, for here we'll call the Hugging Face embeddings, and model name is Mixed Bread AI MXBAI Embed Large V1, the best open source model right now. And in there we are gonna provide the encode keyword argument stating that the precision is binary. Okay, we are making sure that the precision is binary, and here we are creating a vector store known as 1-bit vector store, which will create a face vector store from documents, whatever documents we chunked right now here, based on this embeddings. So what will happen is there will be 1-bit embeddings generated for these documents. That is what will happen in this files vector store creation. Those vectors will be stored. Okay, so we'll also make sure that this 1-bit vector store itself is acting as a retriever with k is 3, which means the top 3 chunks, relevant chunks, are retrieved. Next, for the prompt, we are giving it as prompt template, in which we have said that, okay, answer the following question based on the context provided only. And here there is context tags, where it is starting here, it is ending here, and here is your context. And for this question, which is our question there, try to answer. That is what is the idea of this prompt. And here we have loaded the model chat grok, where you should provide your grok API key. And for model, I have used Mixtral 8x7B32768, and you can use any other models you want, like Gemma or Llama 3, based on your choice. Next, we are creating the stuff document chain, like I said, to combine all of those together, and retrieval chain to answer the question. Okay, so once the chain is created, all we need to do is call the invoke function. Okay, so the invoke function will expect a dictionary input with the value and key pair. Okay, key value pair, where key should be input and value is your question. So I just asked what does the paper introduce, and it says like, okay, it introduces a DSPy system or something like that, and it is fine. Okay, whatever it is said is like, correct only to an extent. And we are more focused on this thing right now. Okay, time. It has taken a total of 1.64 seconds, and the CPU ms is 219. Okay, this is fine, but to know the impact of this 1-bit vector store, we are also loading the 32-bit model directly. Okay, so if we don't provide the encode keyword arguments, right, what will happen is it will try to provide the embeddings in 32-bit, and you will see the impact right now. Okay, we are just creating the normal vector store a retriever, and the retrieval chain is allowed and changed because the document chain expects the model and prompt and not related to embeddings. Retrieval chain only expects the embeddings, so we are just changing the retrieval chain. And if we invoke that, right, the wall time is 2.26 and the CPU time is total 266 ms. You can see, right, there is a difference here, 47 ms there, and the total time was also changed. Okay, that is what is the impact of 1-bit vector store. And to make sure that both the claims are correct, see, now we have seen that okay, it is faster than conventional vector store creation and retrieval. We'll also make sure that the speed is true. Okay, so for this I'm running dir slashes, I guess. Yeah, slashes. Now we need to see the both vector store folder. First is 1-bit, and then the second one is usual. Okay, usual is the normal one. In 1-bit, in both things the pickle size of index will be the same. Okay, because that is just the numbers. What is going to differ is the files extension file name size. Okay, here it is 13,000 bytes, and here it is 106,000 bytes. You can see the difference here, right? It is around 10 times lesser than this, just for 17 pages. But imagine if you did for, let's say, 1700 pages, how much would be the impact, right? So that is the impact of what you will get with the help of 1-bit vector store creation. And in this video, we have seen how to create that. We have seen a theory a bit, and also we have seen that it is faster and it is highly efficient in terms of memory as well. So yeah guys, that's it for this video. I'll see you all in the next video. Until then, if you haven't hit the like button, please hit the like button, and if you haven't hit the subscribe button also, please hit the subscribe button for more videos like this, and share it with your friends so that they'll also be able to create lightning fast rack system. So yeah guys, I'll see you all in the next video. Until then, cheers.